Probability trees, which you may find under the category of compound probabilities, are a way of just representing the likelihood of certain things happening one after the other, whether this is the same event happening again and again, or different events which can just happen in a sequence. For instance, if someone was just to have each letter of the alphabet put on a different piece of paper, and they were going to pick two of these pieces of paper, pick two letters at random, with replacement. That is to say, once they've picked their first letter, they're going to put it back. Now we'll say, what is the probability of it being either a vowel or a consonant? Well, again, we're going to assume y is a consonant. That means there are 5 vowels in our alphabet out of 26 possible letters. This then means there are 21 consonants. So there's a 5 in 26 chance of getting a vowel, and a 21 out of 26 chance of getting a consonant. Given that this person then replaced the piece of paper, the chance of them getting a second vowel is going to be the exact same, because there's still 5 vowels in total, and it's going to be the same for both. And then similarly with the consonant, because they put it back, it no longer matters whether or not they took the consonant in the first place. In the second trial, there is still 21 out of 26. To then get the probability of, say, them getting 2 vowels, you read along the branch from left to right, you're going to be timesing the probabilities together. So 5 out of 26 times 5 out of 26. And if you were to just put that into your calculator, you would get 25 over 676. So out of 676 possible outcomes, in 25 of them you would have picked out 2 vowels. For a vowel and then a consonant, again we're just timesing along the branch the routes that you're taking. So 5 over 26 times 21 over 26. This is going to give you 105 over 676. Again, it's out of the same total because it's all of them out of 26 times 26. For then a consonant and then a vowel, just the 21 over 26 times the 5 over 26. This is actually going to give you the exact same thing, because when you're multiplying fractions, you're just doing top times top, bottom times bottom, and it doesn't matter the order. Then lastly, for the constant, the 21 over 26 times the 21 over 26, this will give us 441 out of 676, which makes sense. It's going to be this massive number just because there are so many more consonants than vowels. You are much more likely to get 2 consonants. But if they then just asked, what's the probability of getting one of each in general, not specifying whether you got vowel first or consonant first, vowel first, consonant second, you can take these 2 middle values and say, well, either of them are technically true. They would fit that criteria. So now that you've timesed along the branches, you're then going to add down the answers. So 105 out of 676, add 105 out of 676. This will just equal 210 out of 676, which, if you just wished to simplify, you could say is 105 out of 338. So that's with replacement. That means the probability didn't change in each given event. But what if it did change? What if we were to get rid of all of this and then say that instead we hadn't replaced the tile? That is, that once you've taken a vowel, there's now 1 fewer vowels left to choose from, and 1 fewer tiles in total to choose from. Once you've picked a consonant, there's 1 fewer consonant left to pick from. Now, our first probabilities, they're going to remain exactly the same. Like, again, to start off with, there are 5 vowels, so there are 21 consonants. But what we're now saying is that the second vowel probability, assuming we took a vowel first, is now going to be 4 out of 25. There's only 4 vowels left, and there's only 25 tiles left, because you've taken 1 in each respect. Consonants, there's still 21 consonants, but now again, it's out of 25. For the vowels down here, though, if you took a consonant first, there's still going to be 5, but that's now again out of 25. And then down here, consonant will have 20 over 25. Yes, so this was for without replacement. At this stage then, we can just do what we did before, times along branches, so we'll have 5 over 26 times by 4 over 25, 5 over 26 times 21 over 25, 21 over 26 times 5 over 25, and then lastly, 21 over 26 times by 20 over 25. These once more, you just put in your calculator, and you will get 2 over 65 for the first one, 21 over 130 for the second. As before, because this is multiplying and they're the same numbers, just the other way around, it's going to give you 21 over 130 again in the third. And then lastly, we're going to have 42 over 65 for 2 consonants. Now, once again, if we just wanted to then combine these, let's say this time it said it wanted at least one vowel. If it's at least one vowel, that's going to be the vowel and a consonant and a vowel, because that's one vowel. But it also includes the double vowel, because 2 vowels is at least one vowel. So if we're adding these together, you've got your 2 over 65, add 21 over 130, add the other 21 over 130. That is going to give you, in your calculator, will give you a combined probability of 23 over 65. So actually, even though the vowels are very much in the minority, the probability of picking at least one of them when you're picking 2 letters is actually just over half. And so we now make space to try a new one. This one I want you to try on your own. So, let us say that there are 10 counters in a box. Of these, 4 are blue. The rest are red. Now, someone is going to take 2 counters without replacement. What is going to be the probability they get at least one blue? If you just try this on your own by pausing the video and then press play when you are ready to compare. Okay, so if we've got 10 counters, 4 of which are blue, that's basically saying that 4 out of 10 are these blues. There's a probability of 4 out of 10. And in terms of the rest being red, that's going to be 6 out of 10. Now, once we have taken our initial counter, if we took a blue first, and without replacement, that means there's only going to be 3 blues left. So 3 out of only 9 left to get another blue. Now, if you took a blue first, you've still got all 6 reds, but again, that's going to be out of 9. If you took a red first, there's still going to be all 4 blues, but that's now out of 9 still. And if you took a red first, that's only 5 out of 9. To then just go along these, because we want at least 2 blues. You've got your 4/10 times your 3 over 9, which is going to be 4 out of 30. And then here with your 4/10 times your 6 over 9 to get a blues and a red, because that's still 1 blue, that's still at least 1 blue. That is going to be 8 out of 30. Here, with the 6/10 times the 4 over 9, that is going to be, once again, the 8 over the 30. Again, these middle ones are going to be the same because it's just the same numbers times together in a slightly different order. And then lastly, down at the bottom, with your 6/10 times your 5 over 9, that's going to give us 10 over 30. Now actually we could simplify these if we wanted. You've got your 2 over 15, your 4 over 15, 4 over 15 and 1 over 3. The point is, if we now wanted to get just at least 1 blue, have so 4 out of 30, add 8 out of 30, add 8 out of 30. That's going to give us in total a 20 out of 30, which then, regardless if you'd simplified earlier or not, now will simplify to 2/3. Okay. With that then, if we're comfortable with these kind of concepts, let's try actual question. Now, in this question, we're presented with 8 cards, each of which has a number on them. Now, this person, Paul, is going to take 3 random cards, and he's going to add the 3 numbers together to get a total T, work out the probability that T is an odd number. Now, even though this question doesn't specify we're going to be using a probability tree, it's still going to be a good way of just representing our information, because once we've taken a card, there's going to be obviously 1 fewer cards left. The probability is going to be changing when we take our next one. This can't be a situation where Paul would be replacing, because if you're adding the cards together, that can't include multiple examples of the same card. If we wanted to draw this out then, we're not going to do it as 2, 3, 4, and 5. That would just be far too many branches. Instead, we'll just worry about whether they're odd or even. So to start off with, for the first couple, we're going to say it's either odd or even. Of these 8 cards, 6 of them are odd. We've got 3, 3, 5, 5, 5, 5. So 6 out of 8 are odd, and then 2 out of 8 are even, the 2 and the 4. Now, after you've taken your first card, you're then going to pick another. Well, again, it's going to be odd or even. Now, if we took an odd first, there's only going to be 5 odds left, and there's only going to be 7 in total left. Whereas with the evens, there'll still be that total of 2, although again, still out of 7. If we took an even first, however, well, then we're still going to have all 6 of our odds left, but now again, that's only out of 7. And then we'd only have 1 even left, so 1 out of 7. Finally then, when we take our third card, and this is just where you have to be mindful of space, because we are going to end up with 8 endings to our branches. From the odds, so if we take an odd and an odd, the probability of getting yet a third odd is now going to be 4 out of 6, and even, there's still going to be 2 evens, but now again out of 6. For going an odd and then an even, to get an odd at the very end is now going to be 5 out of 6, and even is 1 out of 6. To get an even and an odd, then another odd, that's going to be, once again, 5 out of 6, and then beneath that's 1 over 6. And then finally, if we'd taken 2 evens to start with, the probability of getting a final odd, there were still 6 odds to get, and that's now out of 6. There's only odds remaining, so we might as well put it on, but it's going to be nothing. There are 0 evens left that we could pick. Alright, now that we have our tree, we can work out what combinations of these would lead to adding together to make an odd number. If we were to add an odd and an odd and an odd, that would give us an odd answer, right? If, however, we did an odd and an even in any order, that's only going to give you an even answer, because an odd and an odd on their own is even, add another even, yet more even. Odd, even though, again, this can be in any order, just so 1 odd and 2 evens. That's going to give an odd answer, because an even and an even is even, but then add an odd makes it odd. And finally, if it had just been 3 evens, that's obviously going to be even. So these are the 2 ways that we can get an odd answer. So on our tree, the branches that represent either of these, it's the very top one, so odd, odd, odd. Then odd, even, even. Even, odd, even. Or even, odd. These are the 4 endings that will allow us to get an odd answer when you add to whatever the numbers are. It doesn't actually matter what odd and even numbers they are, just by their nature, they will make an odd answer at the end. So for the first one, we'll just have our 6 over 8 times our 5 over 7 times our 4 over 6. For this one, we're going to have 6 over 8 times 2 over 7 times 1 over 6. Down here, we're going to have 2 over 8 times 6 over 7 times 1 over 6. And finally, down here, we're going to have 2 over 8 times 1 over 7 times 6 out of 6. So we're going to work out each of these, and then we'll add them. Plugging these into our calculators, therefore, we get for the first one 5/14. Then for the rest, it's actually all 1 over 28, because they're just the same numbers on the numerators and the denominators just times together in different orders, so it'll end up being the same overall fraction. When you finally add them up then, that's going to give you a grand total, so yeah, we're just adding these, of 13 over 28. Your chance of picking 3 of these cards and adding them together to get an odd number.